Okay, so hello everyone. So today our group will discuss about the recursion and OOP in Python programming. So first is our learning objective first is understand the recursion and famous recursive problems. The second one is know how to use basic OOP and understand its property. So here's a motivational example here. As you can see, this is a famous type of Russian doll, and when you open a big one, a smaller one is inside of it, and so repeat it until the smallest one. Uh, the same goes with the recursion. So as you know, recursion is a programming technique where a function calls itself to solve a problem, and it works by breaking a big problem into smaller versions of the same problem until it reaches a base case, a stopping point. So here's two important part of a recursion. First is the base case is the condition where the function stops calling itself, and it helps to prevent infinite recursion. So the second one is recursive case where the function calls itself with a smaller or simpler version of the original problem, and it must move toward the base case and breaks the problem into smaller pieces. So here's our example of the factorial and a simple mathematic operation. The base case is when n go to 1, and the recursive case is factorial n minus 1. So when to use recursion? So first is when the problem is naturally recursive, because some problems are defined in terms of smaller versions of themselves, such as the factorial, Fibonacci, or the towers of Hanoi. So second is when the problem uses divide and conquer strategies, such as some sorting algorithms here. And third one is when the solution is simpler to express recursively. So few things you need to know before recursion is that you have to the problem have to be broken down into repeatable steps, and you need to define a clear base case and a clear recursive case. So and the problem is defined using repeatable rules. So here, comparison between recursion versus loop, and I'm not going to talk of all of them, but I'm just going to point out a few key difference. So about mechanism, recursion is the function calls itself repeatedly. When loop, it repeats the code with for or while. And the default recursion limit is 1000 in Python, but in loop, it has no limit. So we'll move on to the next part.
Hi everyone, my part is focused on recursive algorithms. Many people think that recursion is magic, but it's actually a method of delegations. It's solving a big problem by breaking it down into smaller and identical versions of itself. But recursions are so very dangerous. If you don't design it carefully, your program will enter an infinity loop and your computer will crash. To fix this problem, we must have exactly two things in our code block and program. The first one is the base case. This is the stop sign. This base case have the program is tell the computer the problems the function will problems will when the problems is smaller enough, it will automatically solve the immediately and we stop. And the next thing is the recursive step. This is the sync rate. The sync rate is when you call the function again, and you must train the input to bring it closer to your stop sign, or your program will run forever and enter an infinite loop. So next, moving to the next thing is our first example, the factorial. The factorial here, right here, we can see that as I mentioned before, we have two things, exactly two things. The first one is the base case, we can call it the stop sign. The next thing is the recursive step. is as a sync rate. To imagine this, we have when we have to know that how is this move. When we call the factorial tree, the program will not doesn't solve it yet. The your computer will post and put that task on a stack of like 30 placed, and then it go to next is the factorial 2, then go deep until it hit 1 and return the values. This is the linear recursions, and it's focused on deep utilizing a stack memory structure. Next is the example B, the Fibonacci. The Fibonacci is quite different, is much different than last example. This is the branching recursions. As it's not like a straight line like a stack memory like last example is calling the function is why it still remains that exactly two things, that the base case and also the recursive step, but the recursive step is more different. It's calling the functions twice in one line, and this creates a tree structure. To imagine this, you guys, when we have Fibonacci 4, it can split into 2, then 4, and then 8. We have Fibonacci 4, Fibonacci 3, then 2, and then Fibonacci 2 split into 2 and 1, Fibonacci 2 split into 1 and 0. Then when it hits the base case, it returns the end values. And this focuses on the breadth, and it creates a lot of redundant work by calculating the same number on different branches, and it makes our computers more have the computer need to calculate more, and many redundant work more too. The next thing we after I mentioned two different examples, you guys have to visualizations about the difference between factorial and the Fibonacci. The factorial is a stack memory. It's a stack like a 30 plate, and the Fibonacci is like a tree. The factorial is dive deep into a hole and climb back out, and you can imagine as it's like a straight line, and the Fibonacci is kind of more different. It's focused on breadth, and it's spread out wider and wider. And at its shape, you can visualize it's shaped like a triangle or a tree. Now, moving to the next part, we will continue to the next part.
Hi everyone. To truly understand about the recursion, we need to look at one of the most famous puzzles in computer science history, the Tower of Hanoi. Legends say that in a distant temple, monks are moving 64 golden discs from one post to another. When they finish, the world will come to an end. Let's look at the right image, the Tower of Hanoi. As you can see, there are three towers here, the left one, the middle one, and the right one, and there will be n discs of unique size on the left post. The goal here is to move all the discs from the left to the right. However, there are some constraints here. The first one is you can move only one disc at a time. The second one, only the uppermost disc from the rod can be moved. And finally, you cannot put a larger disc on top of a smaller disc. Okay, and if you try to move the disc singularly to another post, I think your brain will be hurt here. So that's why the recursive mindset will shine in this case. The recursion is not the thing that will solve the problem, that will solve the whole problem at once. it will just divide the problem into the many small subproblem, and you will solve it consecutively. Okay, and based on my interpretation, do you know how to move those sticks from the left post to the right post now? If you don't know, okay, wait me. I will show you about how to do it. And here, this is Tau of Hanoi figure I have already about yesterday. You can see there are 3 posts: the left post, the middle post, and the right post. And here's the number of the disks. To solve this problem, it's very simple. You just need to follow exactly 3 steps. The first step is you must to put the n-1 disk from the source post to the auxiliary post. After that, you will follow to the step 2, which is move the largest one to the destination. And finally, you just need to put the n-1 disk from the middle post to the destination. Okay, so now you have done it. If you guys ask me how to put the n-1 disk from the middle post to the right post, it's just very simple. It's just to solve the n-1 recursions, and yeah, you just need to divide it into many more small problems. Okay, and based on what I have showed you already, so can you give me the code, like the Python code of this Tau of Hanoi? If you don't know, okay, I will show you right now. Here's the Tau of Hanoi code demo. You need to call function Tau of Hanoi with for attribute and source, auxiliary, and the destination. If n is equal to 1, that is the base case. If n is equal to 1, you just need to move the first stick from the source to the destination. If n is larger than 1, you need to follow the 3 steps as I already mentioned above. And I think you guys have learned about the time complexity and the space complexity. But if you don't know about what is the time complexity and the space complexity of the Tau of Hanoi, I'll show you right now. The time complexity of the Tau of Hanoi is O2 power of n, and the space complexity is On. And before we grab up to the next topic, I will show you the time complexity figure. Okay, and in the slide, there's image of the 2-point n, and you can easily notice that if the n is moving from 0 to the infinity, the graph is just moving like steeper and steeper. That is the reason why when I mentioned at first the case when n is equal to 64, it will take about like a few billion years to move all the disks from one post to another post. To summarize the Tau of Hanoi recursion, it will teach us to trust the process. If you just solve the problem n-1 subproblem, so the whole problem n will be solved. And okay, I have just finished my Tau of Hanoi presentation. So we'll move to the next presentation, the object-oriented programming. Yes.
For the next part, we'll learn about object-oriented programming in Python. So what is the object, you may ask? An object is all the entities with features and behaviors. And in real life, that's basically everything around us. It ranges from unconscious objects to living creatures. Let's take a look at a motivational example. Here we have a wolf and a dog. Both are 2 different objects with 2 different sets of features and behaviors. And as human, we can actually base on those set of features and behaviors to adjust our action towards them. For example, you can decide to pet a dog, but not a wolf, because objectively a wolf can be more aggressive. In reality, we know that both wolf and dog belong to a family called canine. So whenever an animal belongs to a canine family, we should expect them to have these features. So this concept can be translated to a class in programming. And here is a representation in programming terms. So in Python, likewise, an object is basically everything with, instead of saying properties and behaviors, in programming we say an object are entities with attributes and methods. So in programming terms, we have a class canine with two objects, and in Python we call them instances. So from class canine we can instantiate instant wolf and an instant dog. So what is a class now, you may ask? A class basically is a template or a design that we can use to make objects with predefined properties and behaviors. So how to make them? How to make one? How to define a class and make objects from it? Here is a process of defining a class. As you can see, there is a lot of things going on here, but you can just focus on the lines that I have underlined with a red line. The first one is also the most important one, is the class definition. You will use a keyword called class followed by the class name, and notice that for class name we will use camel case, which means that we write the first letter of every word in capitalized form. The second important thing is the constructor. This is very important because it is the one that creates object from a class. So it's put everything together and creates an object from a class that you have previously defined. The third one is the instant method. So this basically is the behavior of our object. And finally, we can see attributes. There are two types of attributes, but we can just agree with each other for now that attributes is the general term to refer to features of an object. Okay, so now that we know all the terminologies, let's remember them because we will refer to them quite frequently. And now let's talk about why we use and learn about classes and objects specifically. The reason we use them is that classes and objects provide us a neat way to organize our data, and they make our code modular, reusable, and very organized. So you can refer to classes as functions. So just like functions where you can define and then use everywhere, you can define a class and then create an object from that class everywhere. And the interesting thing about classes and objects is that every object created from a class can have predefined methods and attributes from that class. For example, if class canine have these three features and instant dog belongs to the class canine, we can also expect instant dog to have the same set of features. But what's more powerful about classes and objects is that we can also modify the attributes of each object with parameters. So we can add a unique parameter to instant dog, is that it's especially cute and friendly to human. Okay, that's enough theory. Let's get to some hands-on practice. Let's get away from the dogs and let's talk about laptop. We will create a class laptop. Remember each of the steps that I talked about. First is the class definition. Use the keyword class followed by the class name laptop. And now we'll just pass, and then I'll make an object from it. I really like MacBook, so let's create one. If I print this object or this instant, it will just show me the memory address, because right now Python is using a default constructor to create this object, and there is no further information. So we can only see this object as a memory address if we print it out. But we can fix that. If we want to add more information to a class, we will use parameters, because a constructor, like I showed you before, is also a method or a function inside a class. So we can go ahead and add some parameters to this constructor, and of course a laptop will have a brand, a model, a price, and the memory capacity. So memory capacity is basically the RAM capacity. And how to access these attributes? We will use a keyword called self. As you can see here, self is also in the brackets along with other parameters, and it literally means this object. So it points to this object. If I write this, it means that I now can access the parameter or the argument that we pass into the constructor brand using self.brand. Self.brand. And I can do the same with other properties and other objects. So now, instead of just printing the object, I can now print the brand, and it will show. Oh, I should update the information of the object first. So MacBook is made by Apple. This model is specifically a Pro M1. The RAM is only 8, which is unfortunate, and the price is surprisingly $1,900, which is prohibiting. If I print MacBook.brand, as expected, it shows the brand Apple. But as customers, we definitely want to see the specs before we decide to buy it, right? So now I will add a behavior or a method to this object. I'll call it show specs dot self, and through the keyword self or this object, I can gain access to every other attributes. So now I will just print this. This code will show the information, so show info of the laptop. And the way you use it is just like using a function. It will be MacBook.showSpecs, open and close brackets. And here we go. So now is a good time to talk about attributes. There are class attributes and there are instant attributes. So think of them as global variable, and the other is local variable, because you can access one with the other, but not vice versa. I'll show you with an example in Jupyter Notebook. So now I have a class attribute called storage outside the method, and an instant attribute called self.brand. If I access the storage attribute with both the class name and the object, this will work. But if I try to access the attribute brand through the class name laptop here, this will raise an error, just like how you expect it to behave with a global and a local variable. And that is the basic that you need to know to use object-oriented programming, or specifically classes and objects. Now we'll go to OOP concepts. I like to refer to them as properties and layers. So now we have covered 2 layers, classes and object, and there's 4 layers to explain. But let's take a top-down approach and learn about these 2 first. The first one is abstraction. because it's very easy. Abstraction basically means OOP will show you the core data and hides the complex information, just like you can drive the car without knowing how the engine of the car works. In our code, we have defined a method called showSpecs, but you can use it with any object created from the class laptop without actually knowing how the showSpec method works. Next is encapsulation. Encapsulation in OOP basically means it binds all the data in a unit with all the methods that operates on the data. Basically means that you can only change the data that is restricted with methods in the class and not outside the class. What I mean by this is that, for example, you want to restrict the attribute price. You need to turn it into something that's called private attribute. That is denoted by the 2_ sign before the attribute name. So if you do this, you turn it into you turn the attribute price into a private attribute, and you will see that if you try to print macbook__ price, it will no longer work because you are accessing it outside the class, the instant method. You are trying to access it directly. But if you try to use the method showSpecs, which also include the private attribute, this will actually work. So basically that's how abstraction and encapsulation work. Now we'll learn more about these two layers, the remaining two layers, and they will be.
So thank you, Hiền, for the explanation on OOB. So now we'll go to advanced topic of OOB. So before that, we have to make a comparison between procedural programming and OOB. So procedural programming is, as you know, it organizes code around procedures, as known as functions, and the function operate on external data, and which is passing in as arguments. And however, OOB organized code around objects which contain state, attributes, and behavior and methods. So here's an example of procedural programming. So, you can look at the code on the screen right here. So we have a function speak animal here. So this code is very simple, but it's not scalable. So if you want to make some modification, you have to edit the code. So this leads to duplicated logic, factorialized code, and poor extensibility. So before we move to polymorphism, this is an advanced topic of OOB. So we have to learn about inheritance first. So we have a parent class here. It is as known as base class. So a parent class defines a general template or interface. It represents the common idea set by all its subclasses. So we have a child class here or subclass. So it inherits everything from the parent class, and it provides its own specific implementation for the parent's method, and it can add new attributes or override existing ones. So now we learn about polymorphism. So you can look at the code here. The make it speak function does not need to know the animal type. So whether the object is a dog or a cat, the right speak method is called. So this eliminates the type checking logic in the function. So if you pay more attention right here, we have a parent class right here. Class animal is parent class, and class dog animal is a subclasses, and the same with cat animal. So polymorphism in one sentence is that the same method can behave differently depending on the object's actual class. So we move on to the operator overloading. So Python allows developers to redefine what built-in operators mean for custom classes. And this is powerful because it makes user-defined objects behave like built-in types, improve readability and expressiveness, and it can also let domains models use natural mathematics notations. So we have several common operator methods include we have
another syntax. To use this, we must define a syntax with underscore. So the first one is add. It defines a plus sign, less than, equal to, get item, and the length of the object. So we have another example here, which is the fetchers class. So the key idea is here. So the key idea is that the add make plus sign meaningful for fetchers, and the equal lets to the fetcher be compared, and underscore represent ensures the vector print nicely. So this small design transform how naturally the class can be used. So instead of defining function vector at v1 v2, we can simply write v1 plus v2. So we also have another comparison of example here. So this is a procedural step example. So this only asks for a rectangle and a circle area shape. So if you want to add a triangle arrow, you must modify this function. So as the system grows, every function handling shapes must be updated. So this will be more complicated in the future. So what if we try to use polymorphism? So the first thing, we classify a class shape here. So I see the first class shape is the parent class, and we have two child class, which is rectangle shape and the circle class shape. And now finally we define a function right here outside the class. So as you can see right here, we will bring the total error right here, and the loop does not take types, and each shape object knows how to compute its own area. And furthermore, if you want to try to add another shape like triangle shape, so it requires no zero changes to the print total error. So you can just add another try class in the class parent class in the parent class. So in this lecture, you will guided to understand recursion, its structure, and classic problems like factorial, Fibonacci, and Tower of Hanoi, and see when recursion is useful and how it compares to loops, and learn the basic of OOP, classes, objects, attributes, and methods. You will also ready to explore key OOP concepts like abstraction, encapsulation, inheritance, and polymorphism. After this, you can also apply polymorphism and operator overloading to make code more extensible and natural to use. So that's all. Thank you for listening to our presentation.